We're on. Some of you are going to go, you didn't cover the last problem. You didn't do the last one. All right, this is going to take about 1 minute. You ready? It's real quick. And then we're going to do a special problem. Special problem, not on the sheet, but you're going to want to know how to do it. Okay? Something in my eye, all right? Something there, okay? Not winking at you. You're going to want to know how to do that special problem. Let's do this one real quick. Okay, Pebbles. Pebbles drives for 3 hours at a constant velocity of 50 meters per second. How many seconds did she drive? This is the easy peasy question. See, everybody's like, problem 5 is going to be really hard. No, it's the easiest one, this piece of cake. How many seconds did she drive? Well, 3 hours can be converted to seconds in one step. If you remember from that video earlier, I told you, if you remember this, if you lots of time, 1 hour is 3,600 seconds. So we can get how many seconds by simply multiplying 3,600 times 3. We don't have to go to minutes first. That's just an extra step. So multiply that out, you'll get 36, 72, 108. Add 2 zeros. Wrong spot. We get 108 seconds is how many seconds Pebbles was driving. Okay? A, done. B. You ready for this one? Easiest one of all. It's a little tricky though. You think it's going to be hard because like 5B, it's going to be hard, right? Ready? Here we go. What was Pebbles' average velocity for the trip? How fast was she going on average? It said she traveled at a constant velocity of 50 meters, 50 meters per second. Constantly, 50. So what's her average? 50. What? That's it? That's it. Okay, see? Easy peasy lemon squeezy. Okay, now, special problem. Special problem. What if you had a problem like this? This one's awesome. Ground. Rocket. I'm making sound effects. That's my rocket engine stuff coming out. We got USA, 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 USA. Rocket. Gonna take off. Okay, what if the rocket engine fires for 10 seconds? So the engine will fire for 10 seconds. During that time of the engine firing, there's an acceleration rate. Now, you don't have this written down anywhere. I'm just making this up, but I like it. I like it. There's an acceleration rate that the engine provides of 10 meters per second squared, or 10 meters per second. So every second that the rocket engine is firing, the rocket is picking up velocity at the rate of 10 meters per second every second, okay? So it fires for 10 seconds. At the end of the 10 seconds, the engine shuts off. So the rocket goes, after 10 seconds of going, shuts off. No more engine. It's quiet now. Shh. Here's a question. How high will go? How high will it go? Sounds like Yoda talk. How high will it go? Help you find it, my will. How high will this rocket engine, how high will this rocket go? How high, maximum height will it go? Now think about this for a second. The rocket engine is going to be firing for 10 seconds as it accelerates up. After 10 seconds, shuts off. Does the rocket at that instant of time, when the engine shuts off at the end of 10 seconds, just all of a sudden now just go and start falling back down? No, of course not. The thing is falling. It's moving at that, we're going to find that out. It's moving fast at that point of time when the engine shuts off, which means it keeps going upwards. Gravity's going to say, come back to me, but it's going to keep going up until finally gravity slows it down, and then it comes back down. We're going to figure out how far it goes all together, meaning during the acceleration time, and then after the engine shuts off, keeps going, stops. What is that total distance? So I'll draw it on here as maybe this is the 10 seconds that the engine is firing. Of course, not drawn to scale. Okay. After the 10 seconds, the rocket engine shuts off. So now the rocket engine at this point is out. It's gone. So you can see we got engine stuff and no engine stuff at this point, but it's going to keep going up. So the question is, how high? All right, so this is really two parts if you look at this problem. This is a level 3 problem. This is like a level 3. Yeah, this is a good problem. So how high will this rocket go? Okay, there's going to be a distance covered during the acceleration time. And then there's going to be another distance covered during the deceleration time because gravity's going to be slowing it down. Let's figure them both out and add them together to get our answer. All right, I'll call this part A. Part B. Part A, what do we know? Write down our physics 5. Acceleration, time, distance, initial velocity, final velocity. Those are the physics 5. Which ones do we know? We know the time the rocket engines are firing during part A, 10 seconds. The acceleration rate of the rocket is 10. Now, some of you might be a little confused by that. Some of you might be saying, well, wait a minute. I thought you said when things go up and down, it's always 9.8. Okay, that's already taken into consideration. The rocket's going to accelerate at 10, which means gravity is already working on it. If there was no gravity, then it would be accelerating at almost 20 meters per second. But gravity has something to say about it. Gravity says, oh, wait, you have to overcome me first. Then we accelerate at 10. So actually, without gravity, we'd be accelerating at a faster rate. But gravity has already done its job. So this is the actual acceleration rate of the rocket. Okay, it's accelerating at 10, going up. Okay, so I put that in here. See, this is why it's a level 3 problem. A lot of things we've got to think about. See, not just so straightforward. No plugging and chugging, I call it, on this problem. But I like it. So the acceleration is 10. Okay, now, anything else? Well, the initial velocity was 0. We did start at rest, so that's 0. Okay. I don't know how high it goes. I need to know that. And I don't know what its final velocity is at this point here when the rocket engines go out. So at this point here, the rocket engines go out, it will be traveling at some velocity. I might need to know that. If we look at our big 3, I've erased them, but look at your big 3. Go ahead and look. We want to find distance here because we want to get the total height. So I want to know what the distance is. Do we have enough information to solve for distance? Take a look at the second of the big 3. D is equal to VIT. VI is 0, so VIT cancels. Okay, get rid of that. Plus 1/2 AT squared. Yeah, you do. We have enough information known already to figure out how far that rocket will travel during the time the engines are firing. So D is 1/2. The acceleration of the rocket is 10 meters per second. And the time that the rocket engines are firing to accelerate the rocket, 10 seconds. And don't forget to square that. Okay. 10 times 10, 100. Times 10, 1,000. Times 1/2, 500. So we will go up 500 meters during the time the rocket engines are firing. All right, we've got the problem I have done. Now we just need to know how high will the rocket continue to travel as gravity is now saying, yes, thank you very much, stupid rocket engines, think you're tougher than me. They were. We accelerated beyond gravity's pull. Yes, we were. But now we don't have those rocket engines. Gravity's like, you're all mine. Come back. So we need to figure out how high it goes during that time when the rockets are off. Okay, what do we know at this point in time? Right here. What do we know right here now that the rocket engines are off? Okay. When the rocket engines are now off, and the only thing acting on that rocket is gravity, we now know the deceleration rate of gravity. So I'll make this a little g is negative 9.8. It will be slowing down due to gravity without no rocket engines overcoming gravity, negative 9.8. Okay, it's going to go up without any rocket engines, stop. Final velocity, 0. It will have a final velocity at its peak, pinnacle, apex, and or zenith of its flight of 0. Okay. Okay, well, let's see, anything else? I don't know what the distance is during this time. Now, we know what the distance is during the part A, but we're figuring out now part B, and I don't know it here. I need to find it so I can add it to my 500, and I'll have the answer. But I don't know it. I don't know how long it's going to take for it to go up and stop. I don't know that. And I don't know how fast it's going at this point. No, we don't. We never figured that out, remember? We never figured that out from the first part. We didn't figure it out. We went directly to solving for the distance it traveled. We didn't figure out how fast it would be going at the end of the acceleration period when the rockets were firing, so we don't know that either. Oh, man. I don't know how long it's going to take for it to go up and stop from here. I don't know what its initial velocity was from here. Oh, that's it. I can't do this problem. Can't do it. I just can't do it. There's no way. Of course we can. We have got to figure out a way. Figure it out. All right, now, how am I going to do this? What could I figure out? What could I figure out? We could figure out, you're not going to be able to figure this one out yet. We don't know this one yet. We can't do this one yet either because any of those two equations with time require a velocity involved, which we haven't figured out. So I need to figure out what the initial velocity is at this point in part B, which was the final velocity for part A. The final velocity for part A is the initial velocity for part B. I need to know that. So I'm actually going to back the truck up and go back to part A because I need to know what the final velocity is of that rocket due to that acceleration in that part. And that final velocity here will be the initial velocity for part B, and I can solve the problem. All right, final velocity of the rocket as it accelerates. Let's go back. Okay, I can erase easy. I know you can't. Sorry. Should have warned you. The acceleration of the rocket was 10. The time the rocket engines were firing was 10. We know the distance is now 500. Maybe we can use that. The initial velocity was 0. Let's figure out the final velocity of that rocket as it gets to this point right here, which I need. All right, final velocity. Anything set up for final velocity? Yeah, we've got the easy equation. I call it the easy, the first of the big three. VF, final velocity, equals the initial velocity, which was 0, plus acceleration times time. The final velocity of the rocket's 100 meters per second when the engines cut out. So that velocity right here is 100 meters per second. That is the final velocity for part A and the initial velocity for part B. Now we're ready. Now we can solve for part B and its distance that the rocket travels. Okay, back the truck up. Beep, 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 beep. The acceleration now for part B is gravity pulling back on it, negative 9.8. The time it takes to stop, I don't know. Actually, don't care. We're not going to need it. The distance I'm trying to find. I'll put a question mark for this one. The initial velocity of the rocket for part B is 100. Final for part A, the initial for part B as it now begins to slow down. So it starts out for part B at 100. It slows down and comes to a stop. Final velocity is 0. So let's solve for distance. Solve for distance, I don't have time. No, we got time to solve for distance. I'm just saying we don't. Okay. Use the last equation. Use the square root one because that doesn't have any time in it. So remember this. Remember that 500. I'm erasing this. Remember 500 for the first part. Remember it. Or we can just write it right here. 500 meters. Okay? Okay. So the last equation, square root equation. Final velocity as we go up is 0. Square root, initial velocity starting from this point was 100. That's 100, and don't forget to square that. Plus 2a, 2 times a, which is negative 9.8, times d, which I'm trying to solve for. Can you see that? You can see that. Okay. Square both sides. Squaring 0 is 0. Squaring this radical gets rid of it. That goes away. That's still 0. So what do we have? 0 equals 100 times 100, 10,000, plus 2 times negative 9.8, negative 19.6 times d. Solve for d, subtract 10,000 from both sides. I get negative 10,000 equals negative 19.6d. Solve for d, divide both sides by negative 19.6. This goes away. Put the d back. Negative divided by negative is a positive. All right. Get her done. 10,000 divided 19.6 equals, distance equals 510.2. I'll leave it at 510 meters. So for part B, the distance is 510 meters. Now, do you remember the original question? The one so long ago, it was like 15 minutes ago, for crying out loud. Long problem, but I like it. Total height, add them together. 510, 500, 1,010 meters. 1,010 meters is how high that rocket will go. I just worked out with the numbers that I used, that this number came out very close to this number. That is not going to happen. I just happened to be in this problem with the numbers I chose. Don't just go, oh, I'll get this and double it. No, don't do that. Okay. If I made this 30 seconds of acceleration, these would be vastly different. Figure them both out, add them together, get your answer. Okay, I like that problem. You're going to see it again. Again, wink, wink, okay? I'm glad you stuck with this video because you're going to be all prepared when the time comes. Night, night.